Hello students, so I'm going to continue the sequence of solving the problems one by one in Timoshenko. So now let's move to the next one, which is problem number 3 on page 54. Show that phi equal to q by 8 c cube into x square into y cube minus 3 c square y plus 2 c square minus 1 by 5 y cube into y square minus 2c square is a stress function, and find what problem it solves when applied to the region included in y equal to plus or minus c, y x equal to 0 on the positive x side. So this problem also involves a polynomial, but here you are directly asked to show that it's a stress function. So we know that there is basically only one condition that we taught you so far to show that something is a stress function, which is that it has to satisfy the compatibility condition, that fourth derivative compatibility condition. And here you are also given the coordinate system y equal to plus or minus c, x equal to 0 and positive x side, which is the exact coordinate system which we had used so far much also the one which I used when we are discussing the theory. Okay, so let's look how you can solve this problem. So I have the handwritten notes scan, so along with the video I will also share you that. So you have the stress function. So you are asked to prove that it's a stress function, which means you have to satisfy this compatibility condition. So it's all about pulling up the respective terms and then substituting it and making sure that this equation is satisfied. So this particular expression is little more involved compared to the last two problems which we have solved, but it's only polynomial, so it's nothing too crazy in it. You just have to take the derivatives and substitute it here. So you expand the bracket and then you take first derivatives with respect to x. So here it will, the fourth derivative with respect to x will come out to be 0, and then derivative with respect to y, and del square 5 by del raised to 4 5 by del x square del y square. So del raised to 4 5 by del x square del y square is 3 by 2 q y by c cube, and del raised to 4 5 by del y raised to 4 is q by 8 cube into minus 24y, which is minus 3 qy by c cube. So if you substitute it in the compatibility condition, you can see that it is identically coming to 0. These two terms will cancel out. They are the negative opposite exact same quantities with opposite sign. So that equation is satisfied, which means it is a stress function. Okay, so first part of the problem is over. Now for the second part, you are asked to determine what type of problem it will solve, and you are given the coordinate system. So again, as we did in the previous problem, you assume that there is no body force, so you keep out body force out of the way. So you can write the expressions for sigma x, sigma y and tau xy in this format as per page 29, which we had already seen. So these second derivatives we have already found that out. So you substitute, you get expressions for sigma x, sigma y and tau xy, and as we had done earlier, you can draw this table format and you can find out the stresses at key locations, its corners and edges. Now sigma y and tau xy. So sigma y, actually it is pretty straightforward. So on the two edges, y equal to minus c and y equal to plus c, you are getting it 0. So it is just like any beam problem. There is no stresses along, or there is no normal stress along y direction. And tau xy is also symbol. So in the case of tau xy, what we see is this is the expression, right? So on the first phase there is no shear stress, but as x increases along the positive direction, you start getting shear stress, and it has a parabolic variation with maximum at the center 3 by 4 q into x by c. So that is shear stress. So normal stress and shear stress, it is something which we have seen in the earlier problems, and it is expected. Here the only difference is this tau xy is a function of x. Okay, so which means at the starting section there is no shear stress. Only that difference is there. Now let's look at the expression for sigma x, which is a little involved and complicated. So here what you see is it is a cubic function of y. Okay, which means the normal stress at any particular section along x direction, it is a cubic function of y. So this is something strange which we don't see, because when we typically use the plane section remains plane before bending, after bending, it is the normal stress along x direction is nothing but a linear function of depth. Okay, so we have never seen it as a cubic function of depth. Even if the loading is triangular, parabolic, whatever complicated loading, sigma x may be a cubic function along x direction, because bending moment may be a quadratic or cubic function. That is possible. Okay, but sigma x being a cubic function with respect to depth, that is something strange which we have not seen it till now. So coming to the question of what type of problem this will solve. So basically this type of problem is also discussed in this chapter of Timoshenko. So as per syllabus, we had discussed only the first few pages of this particular chapter. So if you are interested and if you are curious, you can go to page 46. So let me just go there. See, if you have a beam like this, which is subjected to a general distributed load. So it's not a uniformly distributed load, it's a general distributed load. It can have any distribution. So for such a problem, the approximate formulas for sigma x, sigma y and tau xy has been arrived at. Now if you look at the expressions we got for sigma x, sigma y and tau xy, it is similar to that. Now since I have not taught you this is not part of syllabus. So just try to understand the expressions up to this point. Okay, so the interpretation of for this particular stress function, we'll leave it out, but if you are interested, you can just visit page 46 of Timoshenko second edition and you can read more there. Okay, thank you.